A question that unravels the fascinating tale of construction's silent powerhouse. Beyond being a mere binder, cement weaves through the DNA of our cities. Join us on a swift journey through the absorbing process of cement creation, unveiling raw materials, manufacturing intricacies, and environmental considerations. From masonry to the omnipresent concrete, discover the simplicity behind this complex construction essential. Peek behind the curtain. The story of cement is shorter, crisper, and more intriguing than you might think. But before we jump directly on its manufacturing, let's understand some basics about this magical bond between the building blocks of your home. The word cement can be traced back to the ancient Roman term opus caementicium, used to describe masonry resembling modern concrete that was made from crushed rock with burnt lime as binder. Cement used in construction is usually inorganic, often lime or calcium silicate based, which can be characterized as hydraulic or the less common non-hydraulic, depending on the ability of the cement to set in the presence of water. Hydraulic cement, e.g. Portland cement, becomes adhesive through a chemical reaction between the dry ingredients and water. The chemical reaction results in mineral hydrates that are not very water soluble and so are quite durable in water and safe from chemical attack. This allows setting in wet conditions or underwater and further protects the hardened material from chemical attack. Non-hydraulic cement is less common and does not set in wet conditions or underwater. Rather, it sets as it dries and reacts with carbon dioxide in the air. It is resistant to attack by chemicals after setting. But does the manufacturing of cement as complicated as it resembles? The process of production of cement starts with the extraction of raw materials, which firstly include limestone, clay, and shale. These materials are carefully determined and extracted through delves to ensure the right chemical composition for cement production. Quarrying out all the raw materials is step one of the process. Comprising the majority of raw materials, limestone is a sedimentary rock rich in calcium carbonate. It provides the essential calcium component in cement. Clay and shale add silica, alumina, and iron oxide to the mix. They are usually found in proximity to limestone deposits. Once raw materials are obtained, they undergo mining and crushing processes in order to reduce them to a suitable size. There are many stages of cruising. Initially, the rock is crushed to a maximum of its size, say about 6 inches. Then, through crushers or hammer mills, the rock is crushed to roughly 3 inches. Once the size is obtained for further processing, the crushed material is transported to the cement plant. The crushed raw materials are blended in the right proportions to form a mixture known as raw meal. This step is crucial in achieving the desired chemical composition for the production of high-quality cement. The raw meal is then preheated to enhance the efficiency of the subsequent processes. The preheated raw meal is fed into a rotary kiln, where it undergoes a high-temperature process known as pyroprocessing. During this stage, chemical transformations occur, leading to the formation of clinker. The slurry of finely ground raw material is put into the upper end. A roaring explosion of flame created by perfectly regulated burning of powdered coal, oil, alternative fuels, or gas under forced draft can be found near the lower end. Certain elements are pushed off in the form of gases as the material travels through the kiln. The remaining elements combine to produce clinker, a new material. Clinker emerges from the kiln in the form of grey marble-sized balls. Basically, clinker is a nodular substance that consists of frontage material produced from the kiln. Clinker, after cooling, is ground into fine powder with the use of ball mills. Ball mills are the most crucial and commonly used equipment for grinding. Ball mills are rotating cylindrical drums filled with steel balls that crush and grind raw materials. The grinding process plays a pivotal role in achieving the desired fineness and properties of the final cement product. Clinker and gypsum are taken from their respective hoppers and fed to the mills for ordinary Portland cement, OPC, limestone for limestone cement, and slag for slag cement. Ball mills typically consist of two chambers. The first chamber, or coarse grinding, and the second chamber is fine grinding. The raw materials enter the first chamber, where larger grinding media, or balls, break down the coarse particles. The finer particles move to the second chamber, where smaller grinding media further refine the material to the desired fineness. Each chamber of the ball mill contains a specific amount of grinding media, ranging in size from 17mm to 90mm. The ball charge aids in the grinding process by breaking down the raw materials into finer particles. During the grinding process, additives such as gypsum may be introduced. Gypsum is added to control the setting time of the cement and prevent it from setting too quickly. Other additives, such as grinding aids, may also be used to improve the efficiency of the grinding process and enhance the cement's properties. The ground raw meal exits the ball mill and is circulated to a separator. Not only this, but cement manufacture causes environmental impacts at all stages of the process. These include emissions of airborne pollution in the form of dust, gases, noise, and vibration when operating machinery and during blasting in quarries, and damage to the countryside from quarrying. Equipment to reduce dust emissions during quarrying and manufacture of cement is widely used, and equipment to trap and separate exhaust gases is coming into increased use. Environmental protection also includes the reintegration of quarries into the countryside after they have been closed down by returning them to nature or recultivating them. So have you ever wondered if our cities could rise without leaving a mark on the environment? The concluding chapter in the story of cement is penned with hope and ingenuity. Faced with environmental anxieties and the soaring costs of fossil fuels, nations are rewriting the narrative of cement production. Enter the stage. Reduced footprint cement. A game changer that maintains the functionality of traditional cement, but dances lightly on our planet. The enchanting dupe process introduces us to a world where microscopic allies, bacteria, transform sand and even urine into resilient building blocks, rivaling the strength of conventional concrete. As we witness this transformation, a collective responsibility emerges. The quest for greener alternatives propels us toward a future where innovation meets sustainability. Be an advocate for change. Like, share, and subscribe to stay abreast of groundbreaking developments in eco-friendly construction. Let's construct not just buildings, but a legacy of environmental stewardship. Join the movement, ask questions, seek answers, and be part of the change.